Hi friends, here in this video, I'll be explaining a problem on velocity and acceleration in mechanisms. So, let's get started. Now, here is the question in front of us. It is given in an engine mechanism as shown in figure. Here the diagram is given. Length BC is 120 mm, AB is 250 mm, and XB distance is 120 mm. And as we can see in the diagram, this BC is the crank which is rotating with an angular velocity of omega 75 radian per second and angular acceleration alpha 1400 radian per second square. Then it is given the crankshaft has a speed of 75 radian per second and angular acceleration as explained. Determine the velocity of point X. We have to find out how much is the linear velocity of point X and angular velocity of link AB. We have to find out this angular velocity. Next, acceleration of point X and angular acceleration of link AB. So this is the question. Now, in order to explain this, first of all, I can say that there is this fixed link. I'll call it as link number 1, fixed link. Similarly, here also link 1. Then this is crank BC, link 2nd. Crank BC is connected to this connecting rod which is AB, and that would be link number 3 for us. And this connecting rod AB is connected to this piston which is reciprocating, and that would become link 4. So in short, that is a 4-link mechanism. And now in order to start with the velocity and acceleration part, first whatever the distances are given, like starting with the length of this link BC, I'll be converting it into meters. So it comes out to be 0.12 meter. Similarly 250 mm, 0.25 meter. So when I have converted all the distances in terms of meter, the next step would be angular velocity of the crank is given. Remember, we have to start the problem with the help of the velocity of the crank. So here angular velocity is given and we know the link length. So I can find the velocity of this crank ABC, which is the linear velocity. So linear velocity, since linear velocity of link BC or the crank is given by its angular velocity multiplied by its length. Here I am taking this as 0.12 meter. So that would give me the velocity in terms of meter per second. So angular velocity BC is 75 into 0.12. So the velocity of crank BC comes out to be, it is 9 meter per second. Then after that, now this is the configuration diagram which is there in front of us. This configuration diagram, I am going to draw it again over here and by taking a scale. So the first step in this problem would be step number 1. That is the configuration diagram. In that, since BC is of length 120 mm, AB is having length of 250. So I am going to convert this diagram into a scale of 1:4. That is, I would be reducing the scale here. So configuration diagram is having a scale of 1:4. That is, I would be drawing this diagram on 1:4 scale. For that, this is point C. Angle made by link BC with horizontal is 120 degree. Since the length of link BC is 120 mm, so dividing by 4 it becomes 30 mm. So I would be taking 30 mm in the compass, measuring 30 mm distance. Keeping on point C, I am going to cut this line which is at 120 degree. So I get point B. Then AB distance is 250 mm. So when I divide it by 4, I am getting my answer as 62.5. So taking 62.5 in the compass. Now keeping on point B and cutting this line of stroke. And here this is point A for this piston. Then I need to locate point X. It is at a distance of 120 mm from point B. So dividing this distance by 4 would give me 30 mm. So from point B, I am going to take 30 mm in the compass. And I can say that since this BC distance is already 30, so I'll take the same distance from point B and mark over this connecting rod. Now this gives me point X. So this is the mechanism, and here BC is rotating in a clockwise manner. Then AB is the connecting rod, and here A is this piston. So this piston would be reciprocating along this line of stroke. So here is the configuration diagram, and just now when I have drawn the configuration diagram, the next step would be to draw the velocity diagram. That is the second step. And remember, when we are drawing the velocity diagram, this is the relative velocity method which we are using, and for that the first thing we should know is the velocity of the crank, which we have found out it is 9 meter per second. Now by this known value we can plot the velocity diagram, and for that we need to fix the scale. So how to select the scale, that also I am explaining here. Since the distance is, or the velocity is 9 meter per second, I'll try to fit this 9 meter per second in approximately 5 or 6 centimeters so that the diagram is proportionate and it is visible. So just for an example, I would be fitting 9 meter per second in 5 centimeter distance. So therefore 9 divided by 5 meter per second is equal to 1 centimeter. So the scale becomes, it is 1.8. So this is the scale which I am going to use for velocity diagram. That is, scale is 1 centimeter is 1.8 meter per second. Now after getting this scale, see here I have explained the method how to get this scale so that the diagram becomes proportionate. Now starting with link BC, here at first I am taking a point which is point C, called as the fixed point. So you have to take this fixed point first, and C is here, I can say it is even here, the fixed point C. And now when the link is rotating, link BC or the crank is rotating, its linear velocity component is always perpendicular to the link. So on this link BC we can take any point and draw a perpendicular line. So here I have drawn a perpendicular line. So here this perpendicular line or the perpendicular vector is indicating the velocity of link BC, or we can say the velocity of point B with respect to the fixed point C. So this is in this direction because the crank is rotating in a clockwise manner. If it would have been rotated in an anti-clockwise manner, then this vector would be on the opposite side. Now this vector, the direction of this vector is known to us. So I'll just plot a line which is parallel to this vector. A light line. So here it indicates the direction of the vector, and its value is, since we have taken VBC which is 9 meter per second as it comes out to be in 5 centimeters. The scale is fixed. So here this line would be of 5 centimeters. We can even take it as 6 centimeter, 8 centimeter depending upon the space available. So this is point C and here I'll get point B. This is the direction of the vector. It indicates the velocity for link BC or point B with respect to point C. Next, BC and AB. BC is the crank, AB is the connecting rod. See, at point B, they are having a turning pair, we can say. So when one of the link is moving in this direction, the other link has to move in the opposite direction, like it would be opening. So for example, if VBC is pointing towards this side, then VAB, the velocity vector for link AB, won't be going in the same direction, because at this point B, this link is going to get opened. So here like this, it is a turning pair. So I can say that now the velocity vector for link AB, and again it would be perpendicular, we can take the point anywhere on the link. Now just for an example, see here I am taking the point over here, we can take it anywhere on the link. So here is the velocity vector for link AB pointing upwards and perpendicular to the link AB. Remember to make it perpendicular to link AB. And why these are in opposite direction, again I am explaining. BC is going in the clockwise direction, so its velocity vector is pointing towards the clockwise direction, whereas VAB, since at point B they are joined with the help of a turning pair, there is a pin which is connecting them. So if one of the linear velocity is pointing in the clockwise direction, the other is there in the opposite direction, because it would be opening along this end. So VAB, the direction or the sense is known to us, but the magnitude we don't know for this. So the method would be to plot a line parallel to this, a light line parallel to this, and here this line would be extending up because it indicates the sense of VAB, and the magnitude is not known to us, so I cannot measure the distance directly. Then the hint here is in the form of this piston. This piston is reciprocating, that is this point A, it is reciprocating along this line of stroke, also called as LOS, the line of stroke. So this is an important hint here, that the linear velocity of the piston would be along this line of stroke. So, and that is corresponding to the fixed point C, that is the piston A is reciprocating with respect to fixed point C. Here we have fixed point C, so the movement of the piston would be horizontal, and wherever it is cutting this line, that will give us point A. So extending a line from point C so that it cuts this vector, and here we get point A. So now VAB, we know the sense, it is acting upwards, VAB or the velocity of connecting rod AB. Then C2A, that indicates the velocity of this piston with respect to the fixed point C, also called as VA, the velocity of point A or the velocity of the piston. Now in the question, when we see we have to find the velocity of point X, so for that point X needs to be located, and X we can see here, it is there on this connecting rod AB. So what I would be doing here is, I would be placing point X on this vector AB. So for that, the method which I am using here is by using the concept of similarity, that is, we know the distance BX, so I'll say that the bigger distance BX, that is capital BX, upon the total length which is AB, capital AB, is equal to small bx, which we have to find out, upon small ab, that is what we originally know. So this concept would be used, and out of this bx value is given as 120, ab value is 250 in terms of mm, bx is what we have to calculate, that is the location of point x, AB, I'll measure this in terms of centimeters. It comes out to be 2.7 centimeters. So from this, BX value comes out to be it is 1.296 centimeter. 1.296, approximately we can take it as 1.3 centimeters. So from B, I am going to measure a distance of 1.3 centimeters. So here I get point X located at 1.3 centimeters with respect to point B. Next, joining this point X with respect to the fixed point C. And now this indicates the velocity of point X with respect to point C. So I can write down this is Vx, the velocity of point X. And after that, once we have reached up till here, this velocity diagram gets completed. Now we'll see what is asked in the question. We have to find the velocity of point X. So I'll say that, therefore, from velocity diagram, the velocity of point X, that is Vx, is equal to the length of this vector, which is x to c, or we can say cx, into the scale which we have taken. Now cx distance would be measured in terms of centimeters. It is 4 centimeters. So 4 into scale is 1.8. So therefore velocity of point X, it comes out to be 7.2 meter per second. Now that's the first answer. After that, we have to find out angular velocity of AB. To get angular velocity of AB, first we would require the linear velocity of link AB. So similarly, I can say that the velocity of link AB is this AB distance multiplied by scale. Now AB distance already we have measured, it is 2.7. So 2.7 into the scale is 1.8. So therefore VAB comes out to be 4.86 meter per second. Now after getting the linear velocity, since the question is to find the angular velocity of AB, and for that angular velocity AB is given by the linear velocity divided by the link length of AB, which is the original length which they have given. So here VAB is 4.86 divided by AB. AB is 0.25 meters. So that will give me omega AB, and my answer is 19.44 radians per second. That is the unit of angular velocity. It's the second answer. That is, whatever they have said, the linear velocity of point X we have found out, and similarly angular velocity of AB. Now before drawing the acceleration diagram, remember we have to know the velocity of each of the links which are given in the problem. Like for example, velocity of link BC, that is known to us, it has been calculated. Similarly, velocity of link AB, it is there with us, which is 4.86 meter per second. Now we require the velocity of point A, or we can say the velocity of piston A with respect to the fixed point. So that I am going to find here. It has not been asked in the question, but we would be requiring this velocity in order to solve the acceleration diagram. So for VA, the velocity of piston A is distance AC into scale. Distance AC is 3.3 centimeters. scale is 1.8. So VA value comes out to be 5.94 meter per second. Now once all the velocities are known, we can go for the acceleration diagram, and I'll quickly start that acceleration diagram and explaining the method for that. Now in order to draw the acceleration diagram, that is step number 3 for this problem. For the acceleration diagram, here first of all we have to draw a table. In the first column, I would be writing the name of the link, then its length, and length would be in terms of meter. Next, the velocity of the link in terms of meter per second. Then centripetal acceleration given by a suffix c, centripetal acceleration which acts towards the center, and it is given by the formula the velocity square divided by, we have to take the link length. Then the last column, which is tangential acceleration, and it is angular acceleration alpha multiplied by the link length. Centripetal acceleration would be having a unit of meter per second square. Similarly, tangential acceleration also meter per second square, and this formula we have to remember for centripetal acceleration and for tangential acceleration. That is, centripetal acceleration is given by velocity square divided by link length. Now I'll explain this method in a step-by-step form. Starting with link, first we have link BC, then link AB, after that at last we have this slider A. Now how to fill this table? First of all, starting with link BC, its length is 120 mm, and here we require the length in terms of meter. So BC is 0.12 meter. Then its velocity of link BC is 9 meter per second. Its centripetal acceleration is velocity square divided by link length. So the velocity is 9. So 9 square divided by link length, which is 0.12. So 9 square divided by 0.12 will give me the answer as 675 meter per second square. Then for the tangential acceleration, alpha is required, which is angular acceleration, and here in this problem angular acceleration is given. It is 1400 radian per second square. So 1400 multiplied by the link length, which is 0.12. 1400 into 0.12 will give me the answer as 168 meter per second square. Now after completing for link BC, then I'll go for link AB. Link AB, the original length is 250 mm. In terms of meter, it is 0.25. So remember to take it in terms of meter. So it is 0.25 meters. Velocity of link AB we have calculated, it is 4.86 meter per second. The centripetal acceleration is this velocity square divided by link length, that is 4.86 square divided by 0.25, and the answer is 94.48 meter per second square. Next, this tangential acceleration for the connecting rod AB, the angular acceleration of the connecting rod is not given, so it means we have to find this tangential acceleration, but right now we don't know the magnitude, so this value is unknown. We are going to find this value, and once these much values are known, we can easily start with the further part, that is the acceleration diagram. And for that also, how to select the scale, that I am going to explain it first. Now here we have centripetal acceleration as 675 for BC, for AB it is 94.48, and the tangential acceleration is 168. So selecting the scale in such a way, for selecting the scale, take the major dimension or the biggest dimension here. I can see that 675 is the biggest value. Now I am going to fit this value, suppose around 5 to 6 centimeters, so that the diagram is proportionate. So the scale which I am going to use is 675 meter per second square. I'll fit it into 6 centimeters so that the diagram looks proportionate. So therefore 675 divided by 6, here we have 1 centimeter, so hence 1 centimeter would be 675 divided by 6, 112.5 meter per second square. So this is the scale which I am going to use for the acceleration diagram. I have explained the method how to select the scale. So here 1 centimeter would be 112.5 meter per second square. And now when I am going to start with the acceleration diagram, like in the similar manner where I have drawn the velocity diagram by taking the fixed point C, here also I would be taking the fixed point C. This is the fixed point C. At first we have to look for the centripetal acceleration starting with link BC. So centripetal acceleration is 675, and when we fit it into the scale, it would be 6 centimeters length. And now centripetal acceleration for link BC would be acting towards its center of rotation. Center of rotation for link BC is point C, so its centripetal acceleration would be pointing towards this center C. So that we have to remember. So this is indicating the centripetal acceleration for link BC, pointing towards the center. Now we know the direction for the centripetal acceleration. So drawing a line parallel to this link BC and drawing a light line first. We need to draw a line parallel from point C. The sense or the direction we know here, it is downward since it is acting towards the center. Drawing a light line. Next, this centripetal acceleration value we know it is 675, and I am fitting it into a scale of 6 centimeters. So the length of this line would be 6 centimeters. Measuring 6 centimeter distance in the compass. Keeping on point C, I will be cutting this line. So this line indicates the centripetal acceleration for link BC. Then after centripetal acceleration, we have to go for the tangential acceleration. Its tangential acceleration is 168, and as per our scale, we have taken 1 centimeter as 112.5. So we have to divide 168 by 112.5 to get the value in terms of centimeter. That would give us the value. But just before getting the value, I'll explain the sense in which the tangential acceleration is acting. In order to get the direction for the tangential acceleration, see into the problem, they have given the direction for the angular acceleration. It is also clockwise. So the tangential acceleration would be along the direction of angular acceleration. It means in a clockwise manner. So like centripetal acceleration is pointing towards the center, the tangential acceleration would be perpendicular to it, and it would be along this direction. Why? Because angular acceleration is along this clockwise direction. So like VBC was pointing towards the clockwise direction, similarly this tangential acceleration for link BC would be pointing in the same direction, and centripetal and tangential acceleration, they are perpendicular to each other. So now we know the direction of the tangential acceleration, and remember, whenever in the problem this angular acceleration of the crank is not given, at that time we have to neglect the tangential acceleration. It means only centripetal acceleration is to be considered. But since here in this problem alpha or the angular acceleration of link BC is given, we have to consider the tangential acceleration. Its direction is known to us. Now with the help of this direction, I can plot a line parallel to the tangential acceleration. Here we know the direction of the tangential acceleration, so parallel to it. So this is the direction for the tangential acceleration, and it is perpendicular to the centripetal acceleration. This is the tangential acceleration for link BC, and the value is known to us. How to get this value? It is 168 meter per second square. So 168 divided by the scale, that is 168 divided by 112.5. It comes out to be 1.49 centimeters. So once we get this as 1.49 centimeters, I am going to mark the distance 1.49. It is approximately equal to 1.5. So that is the tangential acceleration for link BC. And the moment we know the centripetal acceleration and the tangential acceleration, this gives me point B. Now joining point B with point C would give me the actual acceleration for link BC. And how to get the direction for this? Now this actual acceleration, when I have connected B and C, is the resultant of centripetal and tangential. Centripetal and tangential are acting along the same sense, we can see here, same direction. So this should be opposing in nature. So now here we have the centripetal acceleration, this is the tangential acceleration, and this is the resultant, which is the actual acceleration of link BC. Its sense should be in the opposite direction, like AC and tangential acceleration are acting in the same sense, so this would be in the opposite sense, because here the arrow is going in the same direction. So for actual acceleration, it won't go in the same direction, it would be from the opposite side. Now this indicates the acceleration of link BC. Then after finding the acceleration for BC, the next step would be for link AB, and for link AB, its centripetal acceleration will also act towards the center. AB and BC are having the common center at point C. So this centripetal acceleration for link AB would also be pointing towards the center C. So this arrow, it shows centripetal acceleration for link AB, and it is pointing towards the common center. So now we know the direction of centripetal acceleration of AB acting towards the center. So point B we already have. So parallel to this link, I'll draw a light line. I'll draw a light line and leave it as it is. Now this light line is indicating the centripetal acceleration of link AB. Its magnitude is, the value is 94.48. So dividing that by scale would give us the distance in terms of centimeters. Scale is 112.5. So 94.48 divided by 112.5, which gives me the value as 0.83 or 83 centimeters. So this is the value of centripetal acceleration of AB in terms of length. Now measuring this length, which is 0.83 centimeters, so approximately that is equal to 8 mm distance, we can say. So on this line I'll be measuring 8 mm distance, close to 8 mm, yes. And this small line, it shows the centripetal acceleration for length AB. Then the tangential acceleration is perpendicular, and now when I would be drawing the tangential acceleration from this point, its direction would be, it can go downward as well as it can go upward. When we are going downward, in order to get point A, we should have the intersection of point A from point C. So the tangential acceleration direction would not be in the downward direction, it has to be in the upward direction perpendicular to it, and the magnitude is not known, so the direction would be measuring 90 degree from this point where I have taken 8 mm distance for the centripetal acceleration. Remember this, measuring 90 degree and drawing a light line which would be extended upwards. Now this line which I have drawn, it is perpendicular to this centripetal acceleration AB, and the vector shows the tangential acceleration for length AB. Now where it is going to cut, that point we don't know because the magnitude is not known to us. Next, the hint which is there for us in this problem is in the form of this piston, that is, the piston is reciprocating with respect to the fixed point C. So its acceleration would be along this line of stroke. So into the table, the length of the piston is not known, the length is not there. The velocity of the piston is velocity of point A, we had calculated it. VA was 5.94 meter per second. And then since it is reciprocating along a straight line, so the centripetal acceleration would be 0 because it is not rotating. And then the magnitude of the tangential acceleration is not known, and whatever the magnitude of the tangential acceleration is there, that same would be the main acceleration. And as the piston is reciprocating with respect to the fixed point C, so here we have fixed point C, and along the line of stroke its acceleration is horizontal, like the velocity was horizontal along the line of stroke. So plotting a light line, horizontal line from point C. Now wherever this line is cutting the tangential acceleration of AB, that would give me point A. Distance C to A would give me the acceleration for point A, or the acceleration of the piston. I'll say it is capital A here. Now after getting this point A, originally we have point B over here. So A would be joined to point B, and that would give me the main acceleration for link AB. Then how to get its sense? For that, centripetal acceleration of AB is acting towards here, we can see with this arrow. Tangential acceleration is acting along the same sense, as we can see here. This is the tangential acceleration of AB. So centripetal and tangential are in the same sense. Main acceleration is the resultant, so it won't be in the same sense, it has to be in the opposite sense. So here is the direction for the main acceleration of link AB. At last, we have to mark point X. Point X is there on this link AB. For that, I'll use the similar concept which I had used for the velocity diagram, that is the concept of similarity. Here capital BX divided by capital AB is equal to small bx divided by small ab. Capital Bx is 120, capital AB is 250, and it doesn't matter whether we take the value in mm, meter or centimeter here because this is a ratio. Then Bx value is what we have to find out. AB value I am going to measure in terms of centimeter, and this line indicates the main acceleration of AB. So I have to take this line, and in terms of centimeter it comes out to be, it is 6.3 centimeter. So therefore Bx value would be it is 3.02 centimeter, or approximately we can say 3 centimeters. So from point B I am going to measure approximately 3.02 centimeters. So this gives me point X. Now once I know point X, I would be connecting it with the help of point C. And that would give me the acceleration of point X with respect to point C. So acceleration of X with respect to C. Now the acceleration diagram gets completed. I'll see what is asked. We have to find out acceleration of point X. So I can say that therefore from the acceleration diagram, the acceleration of point X is equal to the distance xc multiplied by scale distance xc would be measured. It comes out to be 4 centimeters. So 4 into the scale is 112.5, and the answer of acceleration of point X is 450 meter per second square. So that's the third answer. Then the last thing which they have asked is, after acceleration of point X, angular acceleration of AB. And for angular acceleration of AB, we would be requiring the tangential acceleration. And here I can say that since the tangential acceleration of AB is equal to, this tangential acceleration is over here. We have to be careful here. This is the main acceleration, and here this green line, it is showing the tangential acceleration. So measured in terms of centimeter, it is 6.1 centimeter multiplied by the scale is 112.5. So tangential acceleration comes out to be 686.25 meter per second square. After getting the tangential acceleration, since the tangential acceleration is angular acceleration of the link multiplied by the link length, and here the link is AB, so we have to take the length of AB. So therefore tangential acceleration value we have here, that is 686.25. Angular acceleration is what we have to find out, and the original length of link length of AB in terms of meter, it is 0.25. So into 0.25, 686.25 divided by 0.25. Therefore angular acceleration of AB is 2745, and the unit is radian per second square. So that's the fourth answer. And here when we see the question, all the questions have been answered. First we had drawn the configuration diagram, that was step number 1. Step number 2, the velocity diagram. We have found the unknown velocities. At last, step number 3 was acceleration diagram. For that, the table was drawn and then the respective accelerations were calculated. And remember, in case of velocity and acceleration, since this is a graphical method, so the answers may vary from person to person. There may be chances of error here, so we have to be careful, and the answers won't be remaining same for every person. That depends on the scale which we are selecting, on the distances, on how we are measuring, or the values how we are rounding it off. So the answers may change as per the solution which you are solving. So remember, in case of graphical method, plus or minus 10% error is allowed because we are solving it graphically. So the answers may not match exactly. That care we have to take in case of velocity and acceleration in mechanisms. So in short, that was a problem regarding velocity and acceleration in mechanisms. At the end, if you all find my videos helpful, you can like, share, comment and subscribe our channel and share it amongst your family and friends. Thanks for watching.